Are we ready to roll?
Yes, yeah.
Okay, I just wanted to clarify. Welcome everyone to episode 3 of our AI Society's podcast. Today we're looking at AI as a predictive engine across complex systems, from climate weather forecasting to healthcare and clinical decision making. We're joined today by 2 experts working at the intersection of AI and real-world systems. I'm joined by Dr. Hannah, Dr. Sana, I apologize.
No, don't worry.
Whose work focuses on machine learning for climate and weather prediction, including extreme weather events like drought and heavy rainfall. I'm joined here also by Dr. Padman, a clinician and a researcher in digital health and AI, focused on how predictive systems are used in real healthcare settings. I want to get a quick feel of the room. It's lovely to get you all engaged when we are going through these discussions, and so we will do this through a hands-up approach. I would like to get a feel of how many in the room know what AlphaFold is. If you have heard of AlphaFold or know what it is, please raise your hand. Okay, I see about 3 people. Would one of these brave 3 people want to have an attempt at sort of telling us what AlphaFold is, or defining AlphaFold? Absolutely.
Isn't it like you have a chain of like amino acids and you're trying to predict what kind of structure it will turn into, which is like it's very easy to determine what the chain is, but very hard to determine what the end structure is going to be. An AlphaFold is something developed by one of the branches of Google that's basically made real predictions of these proteins.
Yes, absolutely. And the reason that it's so groundbreaking is to do it in the way it's normally done or traditionally done is through sheer guesswork. The way you sort of guesswork what protein structures work together was painstaking and took a lot of effort, took a lot of time. But here we're able to effectively look at different combination of amino acids through the predictive models and are able to save time and improve efficiency within that field. And so that is going to be a very useful reference point as we walk through today's podcast, because it reflects a broader shift that we're seeing across science, from hand-designed models to systems that learn patterns directly from data. Sorry to interrupt the podcast. I don't have a clicker for the slides at the moment. We don't have one? That's okay. We will move it on without the reference of the slides. That is completely okay. We'll now move on towards traditional models versus AI predictive models. One more time, please. Sorry, can we just have one of the subjectives? Thank you. I apologize for that. On the right side is a traditional clinical model. Like the Framingham risk score, it uses a small set of variables such as age, blood pressure, cholesterol, and smoking status. These are combined in a fixed equation where each factor has a pre-assigned weight. The output is a single risk score, and the model only changes when researchers manually calibrate it. On the left, in comparison, is an AI predictive model, similar in concept to systems like the Neurons GCM in climate science. On the left, it shows concepts of AI. What really is NeuroGCM is what we have to answer before we really get into the discussion. It is an AI-enhanced weather and climate model that combines traditional physics-based modeling with machine learning to improve prediction accuracy. Instead of using fixed equation, it's trained on a large data set and learns from patterns directly from within that data. And it captures more complex relationships that evolve as new data becomes available. So to sort of simplify everything that I've said, the main difference is that the traditional model requires intervention. It does not adapt. It is not reflective. Whereas the predictive model continuously adapts to new data that's being present. I'd now like to ask Dr. Sana a question. Climate models like the Neurons GCM replace parts of traditional physics-based model simulations. With learned components, how do you decide which parts of the climate system must remain physically constrained versus what can safely be learned from data?
Yeah.
A long one.
Yeah, sure. So I would draw the line by asking, is that part of the model representing a fundamental physical law, or is it just an approximation of something complex that we cannot represent directly? So physics-based models or climate models are founded or grounded on physical laws like conservation of mass, conservation of energy, Earth rotation, and these laws should be always conserved. We cannot violate them, because if we violate them, the model will look unrealistic or will not be stable. Now, AI can help in these components of the models or components of the climate system where we cannot actually directly represent. We always use approximation, so we don't have a clear equation, and we always use approximation. One example is cloud formation. So clouds form at a very small scale, but they're very important. They're important for precipitation, rainfall, they're important for temperature, they're important for how much radiation is trapped, how much radiation is emitted, but models cannot really represent them well. And they use something called approximation. But AI can learn a better representation by using observations and by using high resolution simulations. So the concept of neural GCM, which you brought, is a physical model, but many of its components where we have uncertainties, or we cannot really know the true equations, or we use approximations. That's where AI was used, and that's why like neural GCM is one of like the famous, or one of the I would say model or a good example of physics-based models. So AI should not replace the physics. AI should help the physics, especially where we have uncertainties.
So that sounds like a lot of side-by-side working together instead of AI replacing what's already the base, which is the physics.
Exactly, and we always need the physical models so that we know whether our AI system is working well, is it realistic,
Of course.
can we trust it?
Of course. That provides good basis to assess accuracy as well as whether it's effective or if it's truly improving the outputs, or whether at times AI can generate outputs that don't compare or might require a little bit of adjustment as well to truly be beneficial. I'd like now to pose a thank you. Just to see if that's working. Perfect. I'd now like to pose a question to Dr. Padman here.
Yep.
Clinical models like the Framingham assume relationships between variables are linear and additive. Where do these assumptions break down in real patients, and what kind of interactions between health factors are often missed?
Yeah, that's a very great question. I see few healthcare workers here, and most of them are non-healthcare workers. I'll just break it down for you guys. First of all, the Framingham calculator has got basic assumptions. The first assumption is they treat risk factors as constant. For example, they treat hypertension same as at age 45 and also at 75, and which we know that it's not true in real life. Secondly, they treat individual risk factors as independent, whereas in real life they are very interactive. So to give an example, obesity in a young, metabolically healthy individual is completely different to obesity in a person who's got depression, anxiety. So that's the second assumption. The third assumption is that they calculate for a single disease, but we all know in real life we interact with multiple disease parameters, multiple health deviants at the same time. For example, postmenopausal women would have multiple risk factors like cancer risk, higher cancer risk, higher cardiovascular risk, higher risk for osteoporosis, bone health, and then higher chances for depression. So this calculator, like Framingham calculators, are quite outdated, but we still use them because they've been tested and tried. Now, what this predictive model does is something beautiful. So if you look at what a generative model or a predictive model does is they switch the speech-based tokens for these disease tokens, and they assign these tokens in a time series analysis, and they produce actual clinical risks. So instead of having one point of time, one disease at a time, you can have a multiple interactive disease prediction over a period of time, and that's what these predictive models does. In spite of their mathematical ingenuity, the key thing for us to note is that they are correlational. They are not causational. So that's one of the important things we have to be aware of. So I think that's where um, the healthcare workers need to draw a line. And even when individuals use these predictive models, they have to be aware that in spite of the brilliant information they can give, they have to be aware that it's not causational. They still have to rely on other tests like clinical trials and health outcome trials for them to understand that better.
Wow, that is really insightful. I'm really interested about these disease tokens. Could you elaborate a little bit more about the disease tokens?
So there was a brilliant study done about a year ago. They wanted to predict the disease outcomes, correlational outcomes for the entire lifespan of a human being. So what they did, they basically used what the generative models have done. So if you look at ChatGPT, I'm just using ChatGPT as one of the examples because I think they popularized the word AI, and they also brought AI to the entire world. So credit goes to the OpenAI company for that purpose. So what they do is something very intuitively well is they predict the next probable words at a new human level. So for example, if when you type in a chat GPT asking the capital city of Paris is, or the capital city of France is, then it automatically pops in Paris. So you think as if it's actually thinking or reasoning or producing the results. What it actually does is they work on the probabilities. So they cut down the speech, the text into several parts, and then they assign what we call as tokens, and then they use large amounts of compute, and then they use that compute and make sure, and then they produce a probability for which words will come next. So that's what they do. So basically, ChatGPT or any generative predictive model does is the probability of what happens next. And what they have done in medicine, in healthcare, is they have swapped these speech tokens into disease tokens. So disease, they have lots of way to classify. One of the way they classify is ICD-10 tokens. It's International Classification of Disease. And now we are at version 11, but version 10 is most widely used. So instead of the speech, they have swapped the speech for ICD-10. So they have put the disease in that. And what that does is it brilliantly, automatically the models correlate the time gap between these tokens and gives us what we call time series analysis. So when, let's say, going back to the example of women's health, a postmenopausal woman who's got a higher risk of cardiovascular diseases, has got a higher risk of osteoporosis, has got a higher risk of depression, higher risk of vasomotor symptoms. If she wants to go and talk to a doctor today, they have one single tool like a Framingham Heart tool where they can only predict one thing. But what they actually need is they are going and asking for answer, if I take an intervention like hormonal therapy, what would my cardiovascular risk look like? At this stage, the traditional tools don't offer that, whereas these predictive tools can offer that answer. They can tell you, yes, you are at a 4% risk if you take uh, hormonal therapy, but if you don't take, then you may be at a higher or lower risk. And that gives them a picture of whether they can take the medication or not. But again, this is just a correlation tool, but still the doctor has to tell you whether it works or not based on the clinical trial. So that's the beauty of these predictive AI models in healthcare.
Thank you, Dr. Padman. That was a very comprehensive and detailed explanation of what tokenization looks like within common models like ChatGPT that everyone has exposure to. By everyone, I really do mean everyone. I assume most, if not all, of the students here or members here have had some exposure to AI due to the relevance it now holds within our society and the way it's being increasingly more integrated in healthcare. So it's really interesting to see how that model has been adapted specifically to healthcare and how tokenization is being brought forward in a new way of application. That's really, really exciting. I would now like to take some questions from the audience, if of course, yes.
Thank you. Very enlightening. So I've got a couple of questions. One for you, Dr. Sana, and one for yourself. I don't know if you can take maybe the answer to John's question so that we can maybe understand it better.
Yeah.
So you talked about the AI having to sort of adhere to the laws of physics, if I understood it correctly. And then if it doesn't, then the whole model would work. How do you, there are, I guess, a huge amount of data that will have to ingest in a certain way, not just separately, correlated. How does the AI do that? How do you, like, from a practical sense, I don't know if that question even makes sense, but how does the AI understand all the laws of physics and then apply them in the right way, practically? So that's my first question. And the second question is, we talked about on the slide, it looks amazing, but then again, practically, in a sort of similar fashion, talked about the correlation between all different factors. How do we teach? How does AI do that in a way that is short of this vast amount of information behind so many walls? In a way that it can actually be useful in the field. So I don't know if these questions make sense or if I'm not asking the right question, but I'd love like a real practical illustration of those two questions. So,
Yeah, absolutely.
Yeah.
Those questions bring out some really important themes. It's very important to know the benefits as well as the limitations
Yeah.
of where these technologies are being implemented.
Yep. So should I go first or you want?
Okay, I'll start. Yeah, that's a good question. So, AI models. When I talk about AI models here, I don't talk about ChatGPT. I'm talking about AI for science. So these models train on data and then predict numbers, output numbers. Now, the training process of AI involves so many layers, a complex architecture, lots of data, supercomputer, GPUs, CPUs, lots of things happening.
And
Lots of time. And all this to optimize the model for the task it's been trained to do. So the data comes into the model, and then the model, by looking at the data, it starts finding patterns, relationships, correlations, autocorrelations. In climate, we usually the data that goes into the model is maps. It starts trying to see relationships between different regions, between different climate variables, between different seasons, time steps. So all this relationship is learned and encoded with weights and numbers and coefficients and mathematical, I would say, like huge mathematical equations and formulas. And the model keeps looking at the data, and every time it looks at the data, it tries to make its own prediction. and then there's a mechanism in the model, AI model, that it starts correcting itself. It knows what it should predict, but at that time, like at this step or iteration, it can't reach that good prediction. So it updates its weights again, and the coefficients and the whole mathematic that's happening in the background gets updated and updated until the model is stable and can predict something that is very close to what we want it to predict at the training. So during training, the model has the task and also can see what it has to predict, and it trains itself to predict this. So basically, that's without using jargons. I'm trying to explain the training process of AI.
So that theoretically makes a lot of sense. My question specifically is practical. Is it prohibitively difficult to do that unless you're a government or a multi-billion-dollar corporation? Or can, founders, which this is what this is about, is that also a reality of doing that theory into practice?
Yeah, it really depends on the data and the task and the region. So you can train a model in 1 minute or even less and do predictions in seconds. But if, for example, you're building a model that needs to ingest data for decades, every hour for the entire globe, then that's lots of relationships. Then that's where the model needs to spend more time to encode and captures all this and embed all these relationships. Then that's where we need not CPUs, GPUs on supercomputers, and we need this model to train over hours, days, could be weeks. But I would say that a common researcher can, for a task, can spend no more than a few hours to train a model that can really solve an important downstream task.
Maybe there's a bit of overlap. There's a large overlap between the questions. But with the healthcare, there's maybe a little bit more complexity because there's other elements, like legal elements and other things.
Yeah, I think with the predictive AI in healthcare, one of the things which we have to be aware is that you don't need predictive models for markers which are already present. So one example is we've got very good biomarkers for diabetes. So HbA1c is a well-studied biomarker for diabetes. You don't need to use that to predict diabetes, right? Where predictive models work is on populations, on areas where it's currently underrepresented. And one of the area, which is the example I gave, is maternal health or women's health in general. And women's health is a very stepwise health. They go from menarche to menopause and postmenopause, and then they go through different different health scenarios in their lifetime. So pregnancy, post-pregnancy, and premenopause, perimenopause, postmenopause. So there is a sequence, but at each sequence, the risk is different, and it varies. But our current tools do not capture that well. So that's the kind of area where predictive AI tools would be useful, not for well-established areas. Like, for example, you want to predict diabetes, you already have HbA1c. You don't need an AI model to
It's
do
a
that.
correlation.
Exactly. You don't need to correlate
So
that.
on a practical, I keep
Yeah.
coming back, and pardon me for maybe holding
Yeah.
the room a little bit. I'm specifically interested in the practical application of the theory
Yeah.
and how difficult or easy, or if there are any major obstacles that you can shed light on
Yeah.
of how to overcome.
Yeah. So
Maybe one of them, pardon me for interrupting, maybe one of them is how to get large data sets, and do these data sets even exist, and do they exist in a form that can be used, and if they do, how does one get them?
yeah. So let's take our example of women's health. So you need a data set large enough which has captured all of women's records from from ideally from menarche to menopause. There are very few data sets which have that. So that's one of your first answers your first question. So if you want to design predictive models, you need to make sure the data represents the population where you are going to test or develop the model for. So that's first thing. So if you look at several large data sets around the world, they'll have something like 45 and up study. 45 and up study, which means above 45. So if I train a women's health model in that, then it becomes less effective because menarche starts somewhere around 12, 13 years. So I missed a big portion of women's health. Like I don't capture pregnancy in that. So my model becomes useless. So you need to be aware of what data set you are choosing for which problem. So that's point number one. Number two, how are you going to validate your data set, right? So the validation data set should be different and also should be generalizable for your training data set. So they both should be different. Your training data set is different, but the data set where you're going to validate, it has to be a little bit more generalized. So you can apply it to your patients or to your end users. Now, once you develop the model, you run through all these brilliant graphs, figures. How do I bring to practice, right? And that's the most important question which you are trying to ask. So I've got these two brilliant data sets. I've designed all of that. I've used good AI engineers, architects. I've got the regulatory authority in place. But how do I bring that in practice? That's a big challenge because our medical training is purely on traditional methods. They have not, doctors, healthcare workers are not trained on AI methods. Patients or end users want answers. They want responses, correlation responses. They want, but our healthcare field is not ready to provide this answer because of the training we have been given. So to answer your question, there has to be a structural shift right across from development, deployment, training, regulatory, for us to bring AI products from bedside to clinical side. So there's a lot of things which are going to happen, which will happen, and one of the things which we have to be aware is it's going to take 10 to 15 years for us to see that kind of change where we will see AI tools in day-to-day clinical practice. So it's going to take a long time.
It's going to be led by Jonas W. founders.
Well, of course, yeah. That's why we are here. Yeah. So we got another question.
Thank you
Thanks.
so much. But we may want to hold off on the questions. There will be further opportunities to ask questions throughout. Some very key points were just raised, and we will get into them further along, such as I believe there is unequal standing here. Climate science definitely has better historical data sets that already exist, such as the ERA5, which I'll get into in a moment. And so yeah, there is a little bit of disparity, and from my own research when I created today's questions for the podcast, it was very apparent that AI is being used in climate science far more than it is being in healthcare. That much is apparent. As for some of the different points that we touched upon, we have many different types of models. Predictive models are one of them. We'll get into real-time adaptive models that correct themselves and generative models such as the disease tokens in a minute. Let's move on. Let's move on towards foundation models across the two domains. What are foundation models? Foundation models are large AI systems trained on broad data sets that can be adapted across many different tasks. We just had a lot of questions about it being adapted for specific tasks, such as the predictive models. The foundation models are different than that. They are adapted across many different tasks. We can see them across domains, from AlphaFold in healthcare to GraphCast in weather and forecasting. Their strength is not just accuracy, it's their ability to generalize these problems. I'll now ask Dr. Sana a question. Many climate foundational models are trained on historical data sets that we briefly touched upon. The ERA5 is a large-scale global weather and climate data set, which has been built over decades of observations and simulations. What risks arise when these data sets contain gaps or biases, as previously mentioned, where we have these gaps where there's not enough data in healthcare for maybe women's health? And especially when these models are being used to predict rare or extreme weather events, how do these biases and these gaps sort of affect the outputs?
Yeah, so ERA5 is an incredibly useful data set. Since we've been talking about data sets, we have, I think in climate we have, and weather we have a lot of data sets. It's never enough, but we have data enough to train an AI model, and ERA5 is one of these data sets. It gives us a consistent global picture of the atmosphere over decades. It combines a physics-based weather model and observations. Now, the issue with observations is that they're not evenly distributed across the world. So we have regions where we have dense networks of observations, and we have regions where we have not that many observations. For example, in the global south, we have less observations than in the northern hemisphere. We have less observations over the oceans and polar regions, and over mountains and complex terrains. And this means that when an AI model is trained on ERA5, it will inherit these gaps. So it means that it might perform better or it might be more accurate over regions where we already had lots of data, but can perform like with less accuracy or not that great in regions where we don't have data. And we sometimes cannot really evaluate the model well when we don't have observational data sets. And that's mainly the issue when we have gaps in data. Now, when it comes to extremes are already rare. So we don't have lots of extremes. These are considered rare events like cyclones or floods or extreme rain or extreme heat waves. So AI is really good at learning the normal weather or the average weather, but it's not great in learning those extreme events. Even physics-based models struggle. So to tackle this, we try to train a model having extremes in mind. So when we train it, we penalize it more if it misses cyclones, extremes, floods. So we really try to make sure that when we train the model, it really pays a lot of attention on these events, so that when we start using it for predictions, it doesn't underestimate those extremes. And regarding biases, we also try to, if we can, to bias correct the data sets before we inject them into the model.
Thank you. That is a lovely answer, and that does actually answer how you sort of correct those biases effectively. I'm just going to follow up with that just a little bit. We've talked a little bit about traditional approaches in healthcare. Climate foundation models can outperform these traditional approaches, but they can be much harder to interpret, perhaps. How important is explainability in climate prediction? And are there situations where understanding why a model made a prediction matters just as much as the prediction itself?
Yeah, that's a good question, and actually it's a big question, and here there might be some trust issues with AI models, AI foundation, more complex AI models, because we cannot see the equations, we cannot interpret them, but it doesn't mean that we cannot evaluate them. So I would say explainability is as important as predictions, especially when it comes to predicting extreme events. So for example, when a model says that there'll be a cyclone, we want to understand or evaluate, is it saying this or predicting this because it just captured some correlation, so it knows that in a particular region and season there is high probability that there will be cyclone, and that's why it's saying there's cyclone, or because it really understand the drivers, the background climate that is leading to cyclone. So we usually evaluate the model, we try to not only evaluate the outcome, but also try to understand, all right, why is it predicting this outcome? Is it consistent with what we expect physically based on the physical system? And this also matters, especially like with when the predictions will be used for real decisions. For example, if there'll be predictions will be used for evacuation or for pricing in insurance, we really need to understand if the model is saying this because that's a possible outcome or just it's picking up some correlations.
Absolutely, that's crucial because climate science and healthcare are really high stakes domain. So is law. These are really high stake domains where if you purely trust or place your trust in that AI output without that having that human discretion of what you might think is most appropriate, you could misguide or misapply your knowledge or the knowledge that comes with AI. That carries its own risks and limitations. We'll now turn to Dr. Padman. In healthcare, foundation models are trained on large-scale clinical data, including electronic health records and
Yep.
imaging, more often. How do we prevent these systems from learning or reinforcing those same existing biases that we've touched upon previously in healthcare access and treatment, and when are they used in practice?
Yeah, that's a great question. So I want to be upfront in acknowledging that you can't eliminate bias in AI models. They are inherent to it. So when I say that, it's how it's the nature of the data itself. For example, you alluded to electronic health records. So if you look at electronic health records, they are basically capturing records of people who actually walk into a hospital system where a healthcare worker, either a physician or a nurse or allied healthcare worker, they note down the patient notes correctly, and it has to be appropriately and accurately coded. And you can see if a person cannot walk into a hospital, their data is not being represented in electronic health record, right? So let's say in a rural area where they don't walk into a hospital where there is EHR, those patients are completely underrepresented. Take another large data set, let's say like a biobank, like a UK biobank. That primarily captures people who are affluent, predominantly who can afford to go and participate in those health systems. And if you look at who get underrepresented, that's a vast majority of people who are not present in the data itself. There's a brilliant paper in Science where they predicted the health outcomes for US population, and they used healthcare cost as a proxy, and they found African Americans were completely underrepresented. And if you look at the data in detail, which means that African Americans they didn't have enough money to even walk into the hospital system for them to even pay for it. So they completely got knocked off the data set. And when you design, train, and develop AI models, you actually are bringing in those inherent biases into that system. So the biases are going to be inbuilt, and there's no way you're going to build a data set which is foolproof, 100% accommodative. Maybe in future that's something which we will think of, but now doesn't exist. But how can we handle this? By training the data to be representative of the population as much as you can. That's one thing you can do. Second, validating the data on a generalized data set. And most importantly, using co-design approaches. That's what we use in our AI research, in our Tribot AI program. We use co-design approach. We bring end users. We want to see what they would like to be represented in a data set. We work on culturally and linguistically diverse population, building a multilingual AI program. We bring in the end user and ask, what would you like to see in that AI system? So that way, that's one way you can, you know, um, alleviate this bias problem. But that's about you can go about with this biases. And you also asked about the explainability.
Yes, we did mention explainability, and
Yeah.
of course it goes across both the domains.
Yeah,
If you'd
yeah.
like to elaborate a little
Yeah.
bit more in terms of healthcare.
Yeah, that's exactly similar to climate, and I think Sana has beautifully explained that. And same goes with healthcare also. AI models are just starting to pop into healthcare system. Healthcare workers just started learning about that. It took me 2 years for me to understand the backbone of what AI model is. Now I'm comfortable talking to an AI engineer about the AI architecture and whatnot. But it took me 2 years as a clinician to come to that space. So it is a long journey. So, but there are few things which anybody can do. First one is asking questions about whether am I able to interpret that AI model, whether am I able to appreciate the transparency of that AI model. So if we can come up with these couple of things, then it should be easy for us. So for example, if I'm using a screening AI model for predicting who will have a higher risk of sepsis, or who's going to have a higher risk of who would need a vaccine, probably like a screening AI tool. It's not a life or death situation. In that models, you can ask for where the models were trained, how it's were validated. But if you're taking the AI model to treatment and making treatment decision, that's where it becomes very tricky. So you really need to understand where the model was, how the model was designed, how it was validated, what the output is, where the knowledge base of the AI model is coming from. So to give an example, we are running a AI program to support multilingual patients in ED triage. ED triage setting is a very high acute setting. You need to be able to make very appropriate triage categorization. So we're designing a multilingual AI tool, but the way we are designing the tool is we have a grounding for our AI model to be giving the answers only from the particular knowledge base. If the model can't understand the question, and if it goes beyond the knowledge base, our model will tell, hey, I can't understand, it's beyond my knowledge base, so you have to talk to a human, right? And we have built strict guardrails where the model will not veer away, and we have a human in the loop where humans will always be the decision maker for the AI tools. So I think if we can build all of these elements, and if we have a couple of explainability tools for healthcare workers, they should be able to discuss about these bias in a confident manner.
Wow, that's a lot to take in. Some really the key and the most key takeaway here that I sort of got from listening to both Dr. Sana and Dr. Padman is that, yeah, bias can't be eliminated. Not at the moment. Not with where the tech is at the moment. Maybe it'll change. And so will these discussions then. These discussions will be reflective of what technology is at the time. This is where it is now, and we must address the limitation as it is. However, there are some measures out there for currently mitigating this bias. Hopefully more measures come to creation as we better evolve with tech and alongside tech. We'll now move on, but before we do, not to put you guys on the spot, but I would like to test your understanding of what we've just gone through. So we've spoken a little bit about foundational models. If I just throw out some common models out there, like Claude, ChatGPT, Gemini, I would like you to raise your hand if you think these are foundation models, or if you think these are generative models. So raise your hand if you think these are foundation models. Okay. Okay. Few hands. Now, who here thinks they're generative models? You think, yeah? Trick question. They're both. They're foundation models and they're generative models. Which brings us to our next section. We will be talking about generative models, which we're more experienced with. But while foundational models, actually I should go into the description as to why they're both. Foundational models, because they're large and general purpose models, they're trained on broad data. And generative models, they produce new content like text, code, and reasoning outputs. But they're not specific for a specific task. They're both general. And that's why ChatGPT, Claude, and Gemini fall under both of those different model characterizations. Sometimes a specific application can fall into multiple different types of model classifications. Let's look at generative AI. Generative AI is very different from prediction or prediction models. Instead of estimating a single outcome, it generates plausible system states that are consistent with learned patterns. In climate science, models like CoreDiff generate high-resolution weather fields from coarse inputs. And in healthcare, similar systems can generate clinical summaries and suggest possible diagnostic pathways. This is a shift that's happening from predicting to generating what could plausibly happen. Dr. Sana, I've got a question for you now. In climate downscaling, generative models produce high-resolution weather fields from low-resolution inputs. When you look at the output of a generative climate model, how can you tell whether it has captured real atmospheric behavior rather than simply generating weather patterns that look realistic?
Yeah, good question. So first, let me explain what's downscaling.
Of course.
A climate model could tell us that over Greater Sydney, temperature is 20. We use downscaling so that we know at every suburb what would be the temperature. So coarse resolution is the climate model, and we use regional climate models or downscaling models to just know the details at specific regions. But for that same temperature that is 20 Celsius degrees, for example, over Greater Sydney, we could have multiple different realizations or multiple different temperatures, possible temperatures over all the different suburbs. And that's what generative AI can do. It can give us all, maybe not all, but it can give us multiple or a range of possible temperatures that correspond to that, to when Greater Sydney has 20 Celsius degrees. Now, before talking about generative AI, the physics-based downscaling model, which are used for downscaling, we already have lots of tools to evaluate them. We use your analysis data sets, we use observations, we use different metrics, we use satellite observations, we use benchmark frameworks, and these same tools that we use to evaluate physics-based models, we can use them to evaluate generative AI models. But the challenge also here is we really want to understand whether not only the predicted map look realistic, we want to see whether the weather behaves really in a physical way. For example, if we're predicting temperature, does the temperature make sense given the elevation, the land surface, the season? Or if it's predicting rainfall also, does it make sense given the season, where we are, when we are? And this is very important. And also we look at multiple variables at the same time. So if you look at the predicted rainfall, predicted temperature, predicted humidity, do all these three together make sense? Like, does the weather behave as we see in the predictions? And because generative AI can produce a range of different predictions, we use some probabilistic methods. So we look at the entire range or the entire distribution. Does it really represent what we expect in that region? Is it physical? Is it the expected range? And that's how we evaluate generative AI in climate science.
Absolutely. Yeah, generative outputs, I think the best way to sort of as you've mentioned, is to pin them against outputs that you currently have, to hold that as the basis of, does this make sense? We'll see. We'll now have a look at what generative AI is sort of doing in clinical settings. It can produce summaries and suggest possible diagnosis. Increasingly, members of the public are using AI tools to interpret symptoms by themselves before speaking to a clinician. That is really concerning, because you can't really trust the outputs, especially of general models like ChatGPT and Gemini and Claude. How do we balance the potential benefits of greater healthcare accessibility with the risks of inaccurate or overconfident medical advice? And what safeguards are needed to ensure these systems remain safe and appropriately uncertain?
Yeah, it's a brilliant question. So I will actually start by posing a question to the audience, and then we'll come back after my response. So my question is, would you trust a friend who lies only 10% of the time? All right, hold that question in your mind. All right, now let's jump into Gia's question. So that's one thing, one word which you have to know about the generative AI models is hallucination.
Is what, sir?
Hallucinations. They will hallucinate, right? Because the basic premise, the basic design of generative AI models are they will hallucinate. They are designed to produce you answers. And so that's something which we have to keep in mind. But one point Gia touched on, the first part, is the accessibility part. I think what generative AI models have done is increased the accessibility to healthcare. For example, imagine a patient in rural area of Australia where there's a severe shortage of healthcare workers, wants to, has a question about his healthcare symptom, and without access to a GP or a nearby hospital, which is 300 kilometers away, right now, generative AI models bridge that gap. Imagine a young person who's got some very personal question about their health problems. For example, their mental health, could be about something about their reproductive health. I think these platforms provide an opportunity to ask that question, right? So if you look at the accessibility point of view, I think these generative models are opening up a wider range of accessibility for populations which won't traditionally come into a health system. So that's the positive side of it. The negative side of it is, the first point is the hallucinations. So you have to know that they will hallucinate, so you can't trust them. And the second thing is, when you walk into a doctor and when you ask a question, when you say, I have fever, I have chest pain, the doctor actually can see you in person, can understand your posture, your behavior, how you react. He or she can check your blood pressure, check your heart rate, take a ECG, right? They can do all of that, and they can provide you some clinical context, and that's something these generative models cannot do. So we have to understand that they can provide some rapid responses, but they don't have any clinical context attached to that. And so we need to be building up some safeguards around how we are going to deal with this. I think in the short term, what we can do is we can have some improvement in the clinical literacy for not just the healthcare workers, but also for the wider audience, of where exactly they should stop seeking the advice of generative AI model, and where they should go and get support from a real healthcare worker. So about a couple of years ago, or maybe 18 months ago, you would have seen in reports that a youngster, a teenager, committed suicide because he had gone to ChatGPT or a similar model, and he had sought advice, and then he had committed suicide based on that. And that's because of the design of the generative AI model. So there's something called prompt injection. So basically, let's say these generative models, they scour all the text in the world, and then they build the probability models. And let's say it has scoured the Shakespeare poem about heartbreak, and Shakespeare says, yeah, you can die instead of living in heartbreak. And then a teenager goes and pops in saying, what does Shakespeare think about heartbreak? Oh, he said to go and commit suicide, or he asked you to come kill yourself. That's the response will come from generative AI models, because they have been designed on that. So you have to draw a line on where you have to stop. These models are very powerful. Only now we are learning about the inner workings of the model. So the terms like prompt injection or hallucinations, it didn't come natural to me. I took a long time to learn, and it will take some more time for others to learn also. But I think in 3 to 5 years, we'll all be very well versed with AI tools, and we will be able to deal with that. And lots of governance rules are now being put in place. Governments are putting guardrails on which models to be released for what purpose. So that's also coming there. And I think in the long term, we all have to understand, especially from a healthcare perspective, the AI models are here to stay. They will be incorporated into our day-to-day clinical work, healthcare work. So we have to learn them, how to interpret them, how to deal with their insufficiencies. So you think about the answer. Would you trust a friend who lies 10% of the time?
Yeah.
Trust that
Yeah.
they're verifying.
Exactly. You'll always check. That's right. That's what you have to do with your generative AI models.
I would trust it, but
But-
not on any
but-
serious advice, you know?
That's exactly
I
right.
wouldn't trust them with my bank details, but I might trust
Yeah.
them with a travel itinerary.
Yeah.
And that's sort of how you might
Yeah.
want to view your usage with generative AI
That's
as
right,
well.
yeah.
You might want to use it for just bringing your thoughts together, but maybe not using whatever output or data it's giving you at face value. Maybe
Yeah.
you want to go check its sources as well. Well, now again, just quickly test your understanding and where you're at. Again, not to put you on the spot, but if I had gone to Claude right this moment, and I've opened it up, and I wanted to summarize a patient's report, my report. Raise your hand if you think that's prediction, or if you think that's generation. Is it generating that outcome, or is it predicting that outcome? Who here thinks it's a predictive outcome?
It's both.
Who thinks it's a generation outcome? Sorry guys, it is not both. It is a generative outcome. And that's purely because the model is producing new text based on learned patterns. So it's going through that patient report. It's not going to give you, it's not predicting anything, really. It's just looking at that text. It's simply summarizing that for you with a new sort of arrangement of words. It's not predicting anything.
But I would think it does both. But anyway, that's a
Trick
it's a
question.
trick question.
It's a
yeah.
trick question.
It does both, yeah.
I was doing the prediction.
Yeah.
You got me there. But let's move on from that. We'll now touch upon real-time adaptive systems. We can have a lovely visual aid for the system that we're going to break down. On the screen is a real-time adaptive AI system, similar to Aurora in weather prediction. It continuously ingests data from satellites, radar, ocean sensors, and ground stations. The data is cleaned, standardized, and used to generate updated forecasts. Unlike the traditional systems, this is a continuous loop. Data comes in, a prediction is made, errors are measured. So this is a real-time adaptive system that is actively correcting itself And then the system adapts and it repeats. And so this is that self-refining machine where a real-time adaptive model is more reflective than any other model we've just discussed. And now we'll see what that's doing in our respective domains. Dr. Sana, in terms of climate extremes like droughts and heavy rainfall, uncertainty is often as important as the prediction itself. How do you communicate uncertainty in a way that's useful for decision making without losing scientific meaning?
Yeah, good question. So let me explain what we mean by uncertainty here. So we know that the climate and the weather is very complex. So if we want to think about what will happen tomorrow, there are a range of things that can happen tomorrow. All right, we're still in winter where there are maybe we don't expect temperature to be 40, but it could be 14, 15, 16, 17. So there are really a range of possible outcomes. And that's what we call uncertainty. Uncertainty is how broad is that range of possible outcomes. So it's not a bad thing. It's actually something we really want to communicate alongside the risk information. So when we want to forecast drought or floods or any extreme weather, we don't use only one prediction. We don't use only one outcome. Usually we look at a range of models or a range of outcomes and we analyze all these together. And we communicate not only what is the most likely thing that will happen, we say that's what we expect to happen, most likely thing will happen, but also we communicate all the different things that can happen. So we really communicate the entire range of possible outcomes. And this is really important for example, councils or emergency service. They don't only want to know what will be the average rainfall for tomorrow. They want to know what is the possibility of floods, for example, damaging flood, and how confident scientists are in this prediction. So briefly, we really want to communicate the entire range, all the possible outcomes, especially the extremes that are really damaging and that we'll try to mitigate or adapt for.
Well, that's really interesting. That's not what I thought was meant by uncertainty in the context, but it's really enlightening to know that by uncertainty we really are looking at the range of possible plausible outcomes. And of course, this also highlights those extremes that are really important to know, because then we can see how far the model is from where the data currently is, or where the outcomes we know are to be the most accurate. In terms of healthcare, Dr. Patman, in continuous patient monitoring, vital signs naturally fluctuate, even in healthy individuals. How do you design systems that distinguish normal variation from early signs of deterioration without generating too many false alarms?
I mean, this is probably the hardest part to design systems. So it's about where you want to place your system. If you place it very sensitive, then you're going to pick up too many deviants. And if you're very specific, then you're going to lose out a lot of people. So that's the hardest part. In the current hospital system in Australia, we have between the flag, we basically capture temperature, heart rate, saturation, your respiratory saturation, and then you put them between two areas, lower and higher settings, and if it goes beyond or above, it gets automatically triggered. But if you see in some patients who have lung disease, you can their saturation by default is lower, and you don't necessarily go and check or act on it even if it's lower in those kind of systems. So that becomes tricky when you use those kind of static systems. In my opinion, AI models are actually better because they produce a continuous series of data points which can actually predict the likelihood of clinical deterioration in a system. So I think in that space, it's very useful. The tricky part is what I said before. It's about understanding or drawing the line between your sensitivities and specificities. At what point you want to be sensitive and what point you want to be specific. And I think that will happen when we do lots of trials, lots of validation studies, lots of calibration. And the most tricky bit for me for AI is in healthcare, how do we integrate these kind of models in the system? How can you integrate into an electronic health record? How can you integrate into your GP record, GP system, right? How can you integrate into your ambulance? Are you going to trust that system? Do you have enough data points, data trials or validation studies to do that? I think integration is probably going to be the major challenge for these real adaptive systems.
So, if my heart is racing from anxiety, if it's if it's racing from some underlying condition where I have irregular heartbeat, how will the model know which is which? Or when should I trust the model? Because my heart could be racing because I'm just nervous to see the doctor. Or I'm nervous to just input symptoms about my symptoms, you know, or the information about my symptom. How do we sort of differentiate there?
Yeah, it's tricky. Like I've been wearing Whoop
Yes.
band for the last 6 months. I'm just I'm in love with that with the data analytics which they provide. It can show my sleep patterns. In fact, my sleep hygiene is improved, and it does show all the heart rate variation minute by minute. It captures every 15 seconds. It's useful, but you have to put it in a context. For example, let's say you have an exam, or you have a podcast, and you want to interview two AI nerds, and you are already forming lots of questions. Of course, that would be that would cause your heart rate to go up, or if you've had too many coffees for your exams, right? So, or you've just rushed into your house after you wanted to run. So it's just not about blindly looking into data and interpreting, but it's about putting that data in the context of where you are, what you're doing, and then making an informed decision. And that's why having AI plus healthcare workers is very crucial, because they provide the clinical context, right? They provide the context for you. And the same thing for personalized decision using real-time adaptive systems. If you're using it, you should develop some context around how you're going to use that, right? So that's where I'll stop.
Absolutely. Now, I did say that the audience will have an opportunity to voice some more questions. However, due to the importance of keeping time and the runtime for the podcast consistent, we might forego those questions in this moment. However, the guests will remain for 30 minutes after the podcast, so you can directly ask some of those questions. I do apologize for that. And that brings us to looking ahead. Looking forward, really. Across today's episode, we've seen AI move from fixed clinical and climate models to foundation models trained on large-scale data to generative systems and real-time adaptive prediction loops. What's changing underneath all of this is not just model performance, but the role of the prediction itself. From something that is calculated once to something that is continuously updated. And within those real environments and those real contexts that we've been speaking about. As these systems move into practice, the challenge is no longer only accuracy, but about how prediction is used under uncertainty, constraints, and that real decision-making pressures in these high-stake environments. To close, I will pose one question to both of our guests, looking forward, what we see. Over the next 5 to 10 years, where do you see the biggest shift in your respective fields? Will AI systems mainly replace parts of existing predictive models, or will they increasingly change how humans interact with and make decisions from those predictions in real time?
Sure. Actually, both. So I see that AI as complementing physical-based models So in particular, they'll be replacing components of these models where where we're not sure about, or we don't have a good representation of the climate system. And I also see, maybe I haven't mentioned this before, but physics-based models are a bit slow and computationally expensive. Now AI, although it might be slow at the beginning when we train it, but once it's trained, it can generate predictions like in seconds. So it's very computationally efficient once trained. And so there is now, like we see now, emergence of surrogate models where AI models are trained to mimic physics-based models. So basically, they try to output what physics-based model can output, but it doesn't mean that AI models are replacing them, because we still need the physics-based model to evaluate the AI, and we need to keep improving our physics-based models so that we build AI surrogates that are also improved. And I also see that um, the way we will have more predictions, because with AI we can predict more possible outcomes, which means that we have more information in our hand, so we can make more informed decisions, especially when it comes to risks or high impact weather, high impact climate. So I think that our decisions will be, climate related decisions will be more informed, assuming that the model is tested well, it performs well. But also, this progress also depends on our capacity to build infrastructures or to improve the current compute infrastructures that is used for research, and also relies on upskilling climate scientists so that they can use AI confidently, and also bringing in computer scientists or AI expert in multidisciplinary research, climate plus AI.
Absolutely. It'll be really interesting to see how all of this unfolds over the next few years. 10 years is a long time, but 5 years, not so much. 5 years go by in a blink. What do you think will happen with healthcare in the coming years?
Healthcare is an exciting field for AI. I think healthcare will have a major impact. Traditionally, we've been stuck to a very population level analysis. We do clinical trials. We develop guidelines based on that. Probably clinical trials are done in US or UK, and then those outcomes or results are applied throughout the world on populations where those trials have not been done. For example, India or Bangladesh. That's what the system is right now. But I think that population level clinical trial data driven approach will change drastically with AI. It will become very individualized. We can provide very granular level information and advice to patients, and I think that will be a tremendous shift in the way we practice medicine. I think in 5 to 10 years, I think that's where it's going to see. Change is going to happen, but we also want to see, to be cautious, and we want to be mindful of where we want the change to be, right? Traditional AI models have been trained in high-income countries in the data from English-speaking population, whereas you know that in the world, English is not the most dominant language, and there are 8 billion people from different continents, different countries. So equity is a major component, and AI is a powerful tool, and if we design it and deploy it well, we can address this equity issue of bringing in underserved, marginalized population, addressing women health, and also community, culturally and linguistic diverse populations. So AI, in a nutshell, is a very powerful tool, and the change is going to happen, transformation is going to happen in healthcare, but I think we should drive it in a direction where we want to see the change.
Absolutely. AI holds a lot of promise and a lot of potential. Today we've discussed not only what you might all refer to as generative models. Today we've looked at traditional models, we've looked at foundational models, real-time adaptive models. So AI is deeper than just generative models. And it'll be really interesting to see how everything plays out as time progresses. That will be the end of our discussion today. Thank you so much for joining us on the third episode of UNSW's AI Society's podcast. Thank you, Dr. Padman, and thank you, Dr. Sana.
Thank you for having
Thank
us.
you.
Thank you. If you guys would like now, you can voice your questions.
Yes.
Ed.
As both of you like challenge your assumptions
Yeah.
at the very end there. I think, so I come from a non-technical background, I'm a law student, but my understanding of AI is that an optimist would say it's actually here to help underrepresented and minority communities, and in instances of climate and sort of the environment, it's ultimately going to help us predict weather patterns and irregularities in communities such as like the DRC, where which experiences the most thunderstorms in the world, or in the Middle East, etc. So, I guess in both instances, right, especially in healthcare, do you really think that as the computational cost of AI and training these models and using these models in particular rises, and as we reach bottlenecks with data centers and GPU and sort of supercomputer usages, etc., right? And we're looking at who the major players are, and how much control they have about which country or which population gets to get access or use these models. Do you think as that cost, both economical and sort of social cost rises or environmental cost rises, do you think that underrepresented and minority communities will still be prioritized and sort of kept front of mind when solving health problems or environmental problems, especially as history has taught us, where money's involved, it's normally underrepresented and minority communities to suffer first,
Yeah.
get cut. So I want to challenge that last assumption because I think you're being very optimistic.
I mean, I'll answer that. Yeah, I think I'm coming from public health background. We want to be optimistic and we want to drive forward inequity issues which are currently in place, and we see AI as a tool, a powerful tool, which can solve some of the problems. And one example I've been giving over the course of the evening is the women's health issue. Currently, we do not have a healthcare setting which can kind of give answers to women. I think AI models can do that in a very granular level, at the evidence-based level. But if we don't design AI models for women's health at this stage, and it's not going to happen. Same thing, if we don't incorporate training data sets or validation data sets from underrepresented, marginalized communities, they will not be used. So the fact that I've trained them, I validate them, that's the population where I'm going to be using it for. So I think one of the things we are trying to do is advocate for AI to be used in those areas, and we write in non-peer reviewed journals, channels. We talk to people in podcasts, media like this, so that people can also go back and think about and how they can, represent for AI models being used for underserved communities. So I'm not being optimistic, but I really want this powerful tool to be used for public good. So take, for example, internet, right? So billions and billions of dollars were invested in the infrastructure of internet, right? So they laid cables all over the world, undersea cables, oversea cables, whatnot. But if you look at it, once internet became pervasive throughout the world, the people who invested in infrastructure didn't really make the money, but it's the others who made the money. But the point here is, for the public good, for the larger use, people, governments, agencies will absorb and they will start using it. But if I don't train AI models for underserved communities, then your point becomes valid, because they get restricted to very fixed population, right? So we need to make sure AI models become like internet. It's widely used across the world in wider settings. Otherwise, then whatever you say becomes true. That gets very restricted to one particular setting or one particular population. Governments trying to manipulate it, and the recent events. I don't want to go deeply, but that governments try to control one particular model. They don't want to release it. So there's lots of things. But I think when we can build AI models for a wider population, for a wider application, then it opens up for it becomes like it becomes available for like a public good, and everybody can use it. So that's where I'm thinking.
Actually, as I was listening to that, and again, this may be an optimistic take on everything, but AI models are cost effective and time effective. So maybe we can look at a possible relocation of resources. If a lot of resources are going into managing these traditional approaches, and if you're able to get back that time, get back that money when these models improve with efficiency over time and get scaled, as we get that time and money and resources back, perhaps we can relocate that effort into diversifying the data set to be more reflective of those populations and those communities that aren't present in data at the moment. So it may be optimistic, but perhaps we are looking at a relocation of resources. Dr. Sana?
Yeah, sure. So first, I'm really proud that when we do our compute, I'm talking about like most of the climate scientists who use AI, we use the National Computational Infrastructure, NCI, at ANU, and it's 100% green, so it runs on renewable energy. It means that we're not harming the environment when running these models or when mostly training them. The other thing that I'll just give an example for one application, which is downscaling, where, as I said earlier, we have global climate models, open source, everyone can access the data, but they give you information for really broad regions, while you need to understand the impact or extremes at particular regions. So we use downscaling. Now, downscaling, if you use physical-based models, so there is one model developed in collaboration with UNSW. It costs to produce its outcomes, like future projections, I would say, what will happen from now until 2100. It costs $1.4 million. Is it one? No, sorry. Either $14 million or 1.4. It's millions of dollars it cost, and it ran on supercomputer for almost 1 year. And this means that only rich countries can afford to build such regional climate models and to do downscaling. While we see that in most poor regions, they don't have this delicacy, they can't produce it, they don't know what will happen at particular locations in the future. They cannot adapt, they cannot plan, they cannot mitigate. So here, AI is a solution, right? Because AI can just with a couple of GPUs, maybe even with no GPUs, can downscale future climate over regions, and look, so people can study extremes and see what will happen in the future. So this is like one from many applications where really I feel that AI is helping, just because our traditional modeling, physics-based model, are super expensive.
Absolutely, I think that well answers the question. Let's take, I think, 2 more questions from the audience. Yes.
I have a question about the climate.
Mhm.
So in the past, climate was relatively stable and therefore very predictable. One of the biases I would be worried about is the data that's being used is collected from the past when we've had more predictable climate. How can we be relatively sure that the predictions about the future aren't going to carry that bias forward when we needed to be able to extrapolate
Yeah, that's a great question. So, when we forecast the weather, it means that we're looking at what will happen after 6 hours to maybe 7 days. And here, we don't, so even if we use historical data, that's not an issue because we don't expect that there will be shift in the climate, shift in the weather, shift in the relationships between all the climate variables within that short time scale. But for example, if we want to see what will happen in 2070, 2080, definitely historical data should not be used to train an AI model for predictions at that time forward. So what we do, rather than training an AI model on historical data, we use physics-based model that can generate the data to the future, and we're sort of confident that it will really represent the physical climate, and then AI would then learn how to surrogate that model.
That put the model at risk of extrapolating the biases of the physical.
Yes, exactly. So the AI model will just perform as good as the physics-based model. But we don't only look at one physics-based model. There are multiple physics-based models, and we try to build AI models that surrogate each of them. So as I said, we look at always at a range of outcomes rather than at a single outcome.
Thank you. We'll take one more question from the audience. Has anyone got any burning questions left? Do the subbies have a question that they would like? Yes.
Yep. Yeah, that's a great question. I think we're already seeing the increase in access of using these generative AI models like ChatGPT. I'm pretty much confident that all my patients who walk into my ED have already done their homework, and then they come to the doctor with their answers from ChatGPT. So that's going to stay because the way our traditional way of going and searching from a web browser has been challenged, and that's been broken, and these chatbots have become very intuitive for us to interact with. So that's going to stay. And people, of all the questions people ask, I think 30 to 40% are health-related questions in everyday conversation. So that's also going to stay. Now, like I told you before, I think we will have to increase the AI literacy for the end user to help them understand where they should stop seeking the answers from ChatGPT and go seek a healthcare worker. And that kind of knowledge creation should happen right across the board, from schools to medias to colleges, universities, in curriculums. That has to completely change because the AI tools are going to stay. From the clinical, from a healthcare perspective, companies are now developing healthcare specific models. For example, Gemini has got a new Gemini healthcare model. Claude has now come up with the Claude specific medical model. What they're trying to do is they're trying to take their large foundational models and fine-tuning with guidelines which have been published for the last 100 years, up-to-date guidelines. And there are lots of companies which are already doing it. So these models are now being fine-tuned with it. So when you pop in an information, at least you would get some credible evidence, and also you can cite the models can cite where exactly they have sourced it from. So the models are going towards that pace. I think the next bit is simply connecting you and the doctor, and which is also happening. So you can just pop in and then say, hey, I want to connect to Dr. Padma. Yes, I'm there. And you can talk to me. So, and I think the way healthcare, the interaction of healthcare, the traditional healthcare interaction is actually completely broken down. So you going to a doctor and doctor advising you of guidelines, that's actually completely getting reshaped. You are now going for your individualized, healthcare advice. I wouldn't even say treatment these days, because it should be more like a healthcare advice, and doctor should be able to, or a healthcare worker should be able to verify that based on your context, based on some of the other elements like getting your vitals. There's one thing which AI will never do, is bringing in the human emotion and empathy in the interaction between patient and doctor. That's something that AI can never replace, and that's only can be done by humans. And that's why, in spite of all the gaga over AI, it's not going to do a lot of damage to humans. Wherever humans are involved, wherever human skills are required, humans will still are going to be there. AI is going to just help us in becoming more efficient and doing things which we have already traditionally done repetitively, which we're already seeing. We are already checking, we are already outsourcing. We've had a brilliant session today, how to generate meeting and agenda with ChatGPT. It's really good. Like, you can outsource. You don't need to do those kind of stuff anymore. You can let ChatGPT do it. All you have to do is understand prompt engineering, and it can do it for you. So certain parts only humans can do, and they are going to stay there. AI is just going to make us a little bit more efficient, and then understand certain parts or elements of healthcare which have traditionally been left out by our traditional settings. So, yeah.
Yeah. Interesting to note, I volunteer at a community legal center, and over the past few months we have had clients come in with their own understanding of what their legal rights are, or where they should be able to take legal action. And the response from the solicitors at the center is just, well, what can I do? They've come in with this perception already, and they're not willing to hear me out. So we'll just have to see how everything turns out over time, I suppose. But thank you, everyone. That is the end of today. Alrighty.